Thank you. Unique ergodicity. So our setting is X is a compact metric space, and T is a continuous map from X to X. And then we have this easy formal definition of unique ergodicity, which is that there's only one invariant measure. But the theorem is that this is equivalent to several other conditions. So let me give you this general theorem. So the following are equivalent conditions. They all hold either they're all true or they're all false. The first condition is there exists a unique T invariant probability measure on X. And of course, this is what we call unique ergodicity. So that's just the definition. The second condition is that when you take a continuous function and you sum it along an orbit, it converges, no matter where you start. So if we take f and c of x, and we form its averages along the first n points in the orbit of x under t, then this converges pointwise to some function. Let me call it f bar of x. I'm not saying what this function is, I'm just saying the pointwise limit exists everywhere. The third condition, you might wonder, how fast does this converge? Maybe it converges slowly for some points and more rapidly for others. Actually, the requirement of pointwise convergence is the equivalent to the condition that there is a continuous function f bar such that this converges uniformly to f bar of x. Oh, and I should say, and this function f bar of x is a constant. Yeah, sorry. I shouldn't call it let me just say converges pointwise to a constant, which is independent of x. And this in fact converges uniformly to a constant, which is independent of x. And then the fourth condition is quite pretty. It says that the continuous functions can all be written as the sum of a real function and a co-boundary. So something that's in the image of the identity minus t, except you have to take the closure. Okay, so I'll amplify these all in the course of the proof, but these are equivalent ways of thinking about what unique ergodicity means. Now, of course, secretly, if there's a t invariant probability measure, we might as well give it a name. Let me call it mu. Then what does this constant c have to be? Well, the integral of Sn of f against mu is constant independent of n because mu is t invariant. So this constant c in both of these things is, of course, secretly just the integral of f with respect to mu. But that's not part of the hypothesis. The hypothesis is just that when you form these sums, you get a constant that's independent of x. And the fourth statement is let me write this explicitly. It says that with a small error, if you take f, a continuous function, you can write it as some constant c, which will turn out to be the same as the c here, plus a continuous function g minus g composed with t. And remember, this is what we call a co-boundary. These things, if you integrate them against an invariant measure, you always get 0. And it's saying that every function is within a constant of being something whose integral is 0 against every invariant measure. So you can imagine that that's very close to unique ergodicity. And so what I should say is we can write f in this form plus, let's call it epsilon of x. And we can make the sup norm of epsilon of x as small as we want. Okay, so f is approximately a co-boundary. Okay, now let's do the proof. The proof, it turns out, is not hard at all. So the proof, in fact, I don't think we've done any hard proofs in this course except for the ergodic theorem so far. So the proof is as follows. So let's observe that, that in fact 1 and 4 are equivalent. And why is that? So what is, let's let mx of t just be the t invariant measures on x. Now what does it mean for a measure to be t invariant? It means exactly that the integral of f against mu is equal to the integral of f composed with t against mu for all functions f. So the t invariant measures are exactly the set of mu such that mu annihilates all coboundaries. So to put it differently, m of xt, of course, these are elements of the dual of c of x star, of c of x, which is c of x star, the space of all measures. There is subspace here. And this subspace is dual to a quotient space. Namely, we take c of x and we mod out by the coboundaries. Because you see, if you have a measure, and you want to test if it's invariant, you just have to make sure it vanishes on all of these coboundaries. That's exactly what invariance means. So mx of t is just the subset of the space of measures that vanishes on the coboundaries. But of course, once it vanishes on the coboundaries, it has to vanish on their dual. And so, sorry, these two things are going to be equal. So this subset m of xt is itself just the dual of c of x modulo the closure of the coboundaries. It's almost the definition of what it means to be a t invariant linear functional. And this is very similar to what we saw in the ergodic theorem, and it led to a very slick proof of the ergodic theorem. Here, it leads to a very slick and quick proof of these other things. Okay, so that's what 1 and 4 are just reformulation of the definition using a little duality in functional analysis. So what about 4 implies 3? So let me do that here. So 4 implies 3. So we want to study the sums of the averages of a function f. So remember that if you take a coboundary and you take Sn of g, if we take this function, then when you form the sum along an orbit, you get a telescoping series. You just get the value of g at the first point and the value of g composed with t at the last point. And you take their difference, you divide by n. So the absolute value of this, when you take the sums along a coboundary, this is less than or equal to something like 2 over n times the sup norm of g. In any case, it goes to 0 as n goes to infinity. The coboundaries are the obvious things that are killed by this summation process. So now we take a general f and we write it as a constant plus g minus g composed with t plus this function that's small. And now what happens when we form Sn of f? What we get is, of course, when we average the constant, we still get the constant again. And then we get something here that's bounded by, in norm, by 1 over n. And then we get something left that's of size epsilon. And so we see that as we sum f, in fact, these sums converge to they get within epsilon of a constant when n is sufficiently large, and so they converge to some limiting constant as n goes to infinity. And then, of course, 3 implies 2, because pointwise convergence is weaker than uniform convergence. And finally, why does 2 imply 1? So to do that, we can one way to do that is to say the following. So let C be any T invariant probability measure. Then, of course, by invariance, we have this great property that the integral of f with respect to C is the same as the integral of Sn of f with respect to C. And now we have 2, so we know that these Sn's converge pointwise to a constant. So this tends to C pointwise. But also, we know that the norm of Sn of f in L infinity is less than or equal to the L infinity norm of f. We're just averaging a bounded sequence bounded by the subnorm of f. And so these integrands are also bounded. Why do I like that? Because the dominated convergence theorem then says that if this goes to this pointwise and everything's dominated by a bounded function, then the integrals also converge. So since this function converges pointwise, this integral tends to the integral of C with respect to the measure C, which is just this constant C. Now, of course, the constant C depended on f, but it doesn't depend on C. So in other words, the conclusion is that the integral of fc is the same for all C, for all invariant probability measures, and for all f. But that's the same thing as saying that there's, in fact, only one point in Px of t, because a measure is uniquely determined by its integrals against all continuous functions. So this implies C is unique. Okay, so that's a little glimpse into some of the ways you can think about uniform unique ergodicity. This rather weak statement here too implies this quite strong statement that f is almost a constant plus a coboundary. And by the way, if you want to know when f is almost a coboundary, the answer is it's if and only if it integrates to 0 against this unique invariant measure. Okay, so let me come back to one of my examples of a dynamical system that's not uniquely ergodic, because I want to present you with an open problem. It's nice to have elementary open problems to indicate that this field is still very rich and active. So our first example, of course, was that the irrational rotation T on S1 is uniquely ergodic. And then we have another example, which is that if we look at T of x equals 2x mod 1 on S1, the doubling map, this is very far from being uniquely ergodic. All the periodic points, of which there are many, provide discrete measures which are invariant under T and even ergodic under T. Although Lebesgue measure itself is preserved and T is ergodic with respect to Lebesgue measure. So here's the open problem. This is due to Furstenberg. And I would, in some sense, Elon Lindenstrass earns the Fields Medal a couple of ICMs ago for making progress on this problem. Not solving it, but making some substantial progress and its many variants. So one thing to notice is that if we think about this example, it didn't matter if we put 2 here. We could have put D here for any D greater than 1. It's definitely not going to be uniquely ergodic. So what Furstenberg asked is, what if we take 2 of these transformations? And instead of asking for a measure that's invariant under the first or the second, we ask that it's invariant under both. Now, there are some measures that are invariant under both because these transformations permute the points of finite order on the circle. They permute the nth roots of unity, or rather map them into themselves. And so it's easy for them to have periodic cycles in common. But aside from that, the only obvious measure that's invariant under both is Lebesgue measure. And so the open problem, which goes in the business under the name times 2 times 3, and it's not x, it's times, is to show the only non-atomic ergodic measure. Well, let's say measure on S1 ergodic and invariant for both times 2 and times 3 is Lebesgue measure. Okay, so that is the statement of Furstenberg's conjecture that basically, when you start with a transformation that generates an action of z, well, if it's sort of hyperbolic, this one is expanding because d is bigger than 1. It has lots of periodic points, so it's not going to be uniquely ergodic. But what if we take an action of 2 commuting transformations? How much richer is Z2 than Z3? Well, it's not quite Z2. It's more the semi-group generated by times 2 and times 3. But in any case, it's an abelian group. The 2 transformations commute. That larger dynamical system is conjecturally very close to being uniquely ergodic. If you throw out the atomic measures, then in fact, there's only one measure invariant under both. Okay. So as long as we're discussing open problems, let me also remind you that a nice property related to unique ergodicity is the idea of uniform distribution. This is a property we can formulate without reference to any dynamical system. We're just given a sequence x0, x1, x2 in the circle, for example, or in any space. And we're given some measure mu, say Lebesgue measure. Then we say this sequence is uniformly distributed if, so xi, it's ud, if for all intervals j contained in S1, we find that the number of I less than or equal to n, such that xi lies in this interval, divided by the length of the interval, where the length of the circle is normalized to be 1, tends to, divided by n, tends to the length of the interval over the length of the circle. And this is equivalent to saying, if you prefer integration, that if you take a continuous function and you do the obvious thing, namely you take the average of its values at these points xi from 0 to n minus 1, then this just converges to the interval of f of x dx over the circle with respect to the measure of total mass 1. Okay, so what sequences do we know are uniformly distributed? We call them xn. So the first, of course, our favorite is the sequence n alpha, where alpha is an irrational number. This, of course, means these numbers mod 1, the orbits of 0 under an irrational rotation of the circle. Now, I almost assigned this as a homework problem, but I think I'm not going to, but you might want to think about it. It's quite an interesting thing to try to prove. It's also true that n squared alpha mod 1 is uniformly distributed, as long, of course, as you make sure alpha is not a rational number. And that's not quite as easy as this proof. There's not a dynamical system present here, or at least an obvious one. And in fact, the same thing is true for any integer k greater than or equal to 1. And there's even more general theorems one could formulate where you replace this by some sort of polynomial in n. But I won't try to formulate the more general statement. I just want to give you a sense of what goes on. Another nice circle of questions is around if we take a lambda greater than 1, what can we say about the sequence xn is lambda to the n mod 1? The fractional powers of the fractional parts of powers of a number bigger than 1, zipping off to infinity, getting larger exponentially fast. So one theorem that's not too hard to prove is that this is uniformly distributed for almost every lambda. So let's look at some specific lambda. One lambda I like is the golden ratio, 1 plus the square root of 5 over 2. Is this sequence of powers of the golden ratio uniformly distributed mod 1? Are there fractional parts evenly spread out between 0 and 1? Who knows about the powers of the golden ratio? If you don't know, you might quickly open Mathematica and compute the 10th power of the golden ratio.
Sorry, Kurt, can you repeat the question?
The question is, are the powers of the golden ratio uniformly distributed mod 1? How do they behave mod 1? What do their fractional parts look like?
I think, do they converge to 0 mod 1?
They do, in fact, converge to 0. Do you want to explain why?
Yeah, I think the point is that for the golden ratio, it's a Piso number. So it's Galois conjugates, in this case only has one other one, have modulus less than 1.
Okay.
And this is important because you can make an argument where you embed the ring of integers for the golden ratio into a lattice and at the different places of this number field associated to lambda. And then the multiplication by lambda in these other directions in the lattice, different Galois conjugates will be contracting because the conjugates have modulus less than 1.
Okay, good. Anyone else want to try to sum up why the powers of the golden ratio get closer and closer to being integers?
So I guess to put it in a more elementary kind of like language, the sum of nth powers of all Galois conjugates of an algebraic integer must be an integer. So I think for the golden ratio, you get something like the Binet. No, sorry, the Lucas numbers. Yeah.
Okay, but in any case, they are integers. Why are they integers, though? And what are, after all, this is just a quadratic number. What are you really saying?
Yeah, I think because lambda to the power of n plus lambda bar to the power of n. It's an integer, and when you multiply 1 and lambda bar, the absolute value of lambda bar is less than 1, so you get something like.
Okay, so why is lambda to the n plus lambda bar to the n an integer? What do you call that
because
number?
those are Galois conjugates of each other. Like they are the trace of the.
They are also Fibonacci number.
Sorry.
I think aren't they Fibonacci number?
It would be helpful if everyone turns on their videos, but especially those who are talking. Okay, so say, you think that they're Fibonacci numbers?
Yes, I think the sum over 2 maybe is Fibonacci number, or just the sum.
I think that would be wonderful, but it's not quite true. But something almost like that is true. But what we're talking about is the following. What kind of a number is gamma? It's not just an algebraic number. It's an algebraic integer. It has the property that gamma squared equals gamma plus 1. So it satisfies a monic equation with integral coefficients. So gamma ratio is an algebraic integer. In fact, it sits inside a Q adjoint the square root of 5. And inside of here, if we call this the field K, the integers in this field, often denoted by OK, are in fact generated by gamma. And it's an algebraic integer because, as I said, it satisfies gamma squared equals gamma plus 1. In other words, it's a root of the monic polynomial x squared minus x minus 1. Okay, now this field is a quadratic extension of Q. It has a Galois conjugate operation on it, and the Galois conjugate of the Galois group is, of course, Z mod 2, and the Galois involution sends square root of 5 to minus square root of 5, which it turns out sends gamma to minus 1 over gamma. And now the main point here is that when you have an extension of fields, you have a lot of nice maps that bring you back to the original field. One of them is the norm, where you take the product of all the Galois conjugates. The other is the trace, where you take their sum. And both of those operations send integers to integers, because the integers form a ring. So if you take the set of all algebraic integers in the world forms a ring. So gamma plus its Galois conjugate, that's a sum of 2 integers. So it forms a ring. It's an ordinary integer in Q. And so what we find is that gamma to the n plus gamma prime to the n is an integer. And so gamma to the n mod 1 is equal to gamma prime to the n mod 1 with a minus sign thrown in. But the product, the norm, gamma times gamma prime is equal to minus 1. So since gamma is big, 1.6 something rather, gamma prime is small, it's like 0.6 something rather, with a minus sign. And so the powers of gamma prime tend to 0. And so gamma to the n tends to 0. So remarkably, the powers of this particular quadratic irrational get closer and closer to the integers. So they're not an example of this phenomenon where almost every point is supposed to have powers that are uniformly distributed. And in fact, it turns out to be much easier to give examples where things are not uniformly distributed than where they are. So as was mentioned, there's something called a Pizot number, and this argument extends immediately to show that they also have the property that they tend to the integers as you take higher and higher powers. So here's another open problem. Suppose lambda is a real number greater than 1 lambda to the n mod 1 tends to 0 as n goes to infinity. Then, does lambda come from one of these algebraic constructions? And it's known that if it's an algebraic number, it has to be a Piso number. So we can just ask, then is lambda algebraic? So this problem is still open. In fact, it's been open, I know for sure, for almost 40 years, because when I was in graduate school, I thought I would write my minor thesis on this problem and solve it very easily by proving that there were uncountably many numbers with this property and only countably many algebraic numbers. But it turns out, as I learned when I wrote my minor thesis, there's a proof that there are only countably many numbers with this property. But it's still not known if they're algebraic. Here's another problem in this circle of ideas that's open. Are the powers 3/2 to the n, are these even dense mod 1? The most specific numbers you can think of for which you don't have an argument like this Piso number argument presumably have the property that their powers are dense, and yet many of those questions are open. Okay, so that was a little intervention into a little cultural aside about uniform distribution in general. Okay, so now I want to return to a theorem I stated at the end of the last lecture. And this is something I often do by accident, and I occasionally like doing on purpose, namely stating theorems that are just false. So this theorem is false. So let U be an open set and alpha an irrational number, then the limit as n goes to infinity of the number of k such that k alpha is in U, and k is less than or equal to n, and divided by n, so the percentage of time that this irrational orbit, rotation orbit, spends in U converges to the measure of U, or if you like, the measure of U over the measure of the circle. In other words, I wrote down several definitions of uniform distribution. One of them was about intervals, one of them was about continuous functions, but I did not write one down that was true for arbitrary open sets. So let me write this down. And now let me put quotes here. So the statement is that this is false. The question is how to fix it. How can you change this statement so that it becomes a natural statement that's true? And by fixing it, I don't mean just replace U by an interval and then say we already proved that. That's the fix. There should be some property that about open sets which makes this theorem true. Another way to think of fixing it is you might say, for what discontinuous functions can we assert that, so when does Sn of fx tend to the integral of f dx beyond the case, pardon me, beyond the case where f is a continuous function on the circle. But we want this to be true for all x, not for almost every x. That's what would be guaranteed by the ergodic theorem. Okay, so rather than answering that question, I'll have you answer it. So the measure isn't obvious, says Yang Shengang. So the measure is uniform measure on the circle. That's why I wrote dx here. So it's always, you know, it's the same thing as what should happen for uniform distribution. So let's go to breakout rooms for about maybe a little less than 10 minutes. As usual, please introduce yourselves, pick a reporter, and then try to find answers to these questions. Try to find an example of an open set U, showing this is false, and try to find a way to change the statement of the theorem so it becomes true. Okay, so let me try this. Okay, hang on a sec. Okay. Okay, so please go ahead and join up your room. So I'm thinking in the future, actually, you guys might as well go ahead and join up the breakout rooms also. You're all contributing to the discussion nicely and seem to understand what's going on. And you know, I doubt you're not going to dominate any of the discussion. So feel free next time. In fact, if you want to go to breakout room now, feel free to just go ahead and jump in. I'd actually enjoy having you to be part of the discussion, maybe to move it along a little if people get stuck.
Thanks, appreciate it.
Okay. Okay, everyone should be back. So raise your hand if you're a reporter. So Jonathan, do you want to weigh in?
Yeah, so we came up with a counterexample, which is to look at an interval of length epsilon around alpha. and then an interval of length epsilon over 2 around 2 alpha, and epsilon over 4 around 3 alpha, and so on. Fraction on the left-hand side is always 1, and then if you make epsilon small, these are vanishingly small collections of intervals.
Great idea. So you can let U be a union of, say, the ball around n alpha of radius epsilon times 2 to the minus n, and then the measure of U is approximately epsilon, but the whole orbit of alpha, this contains alpha, 2 alpha, etc. And so this density function goes to 1, even though the measure is epsilon. And this U is, of course, so what it's an example of is something that seems maybe slightly paradoxical when you first do measure theory. Namely, U is a dense open set, and yet its measure is very small. So it's sort of big in the sense of topology, but small in the sense of measure theory. And that's what sort of the coexistence of those two phenomena is why this statement is not quite right. I don't see any other. Oh, Michael Curl, do you want to weigh in? Maybe you have a different. Yeah.
Yeah. I mean, our example was basically the same for the first part. Yeah.
Okay. How about an idea for how to correct the statement of the theorem?
Yeah, we weren't exactly sure, but an idea we had was maybe we need some condition about the closure of the open set. So in particular, in this case, the measure of the closure of the open set is the whole thing, which is too big. So maybe if the measure of the closure of the open set is the same as the measure of the open set itself. Excellent.
So in fact, that is a sufficient condition to get this to work if you require that the measure of the boundary of U, which is, after all, the difference between its closure and the set itself, if the measure of the boundary of U equals 0, then in fact this becomes a true theorem. So if we add here plus the measure of the boundary of U equals 0, then this theorem becomes true. And in fact, there's a notion that predates the notion of measure called content. Content is what you get when you try to approximate the measure of U by covering it with finitely many open intervals rather than countably many. And if the content of U comes out to be the same as the Lebesgue measure of U, then in fact the theorem works, and that's equivalent to the boundary having measure 0. Another reporter, we had lots of breakout rooms. No other reporters? Yes, Tina.
I think we did the same. We did the same construction for counterexample, and also for the second part, we were saying that so this is true. We know that we have this equidistribution for continuous function. So we were trying to see for which open set the characteristic function is. We can approximate that by continuous function. And we were also, so we didn't solve that, but we come up with that idea that this boundary point of this limit point of open set is important. And we guess also that it should be, maybe if it's a measure 0, it's work. If it's measure 0, we can approximate that by continuous function, but we don't know, is it necessary condition or not?
Okay. What about this question? So the question here was, when can we assert that the sum over the orbit of x of f converges to the integral of f for all x, not just for some x? And we know it's not enough to assume, say, f is measurable, because you could take f and change its values on the countably many points in the orbits of x, make them all 0, and then the sum would come out to be 0 there, and it would have nothing to do with the integral of f. So this, for this question, it's enough for f to be continuous. It's not enough for f to be, say, an L1. Is there some intermediate class of functions where this works? Does anybody have an idea? So Tina brought up an important point, which is that if you could take your function u, your set u, and approximate its indicator function above and below by continuous functions in a good way, then you get the desired result from the result for continuous functions. So when I have an f that might have all sorts of weird behavior, at least not be continuous, when can you approximate f nicely from above and below by continuous functions? For example, the indicator function of the rationals is bad in this way. Is if you try to approximate it from above, the values have to be at least 1, and from below it has to be at least 0. But in fact, if you have an interval, you can easily approximate it from above and below by continuous functions, its indicator function, and the same in fact holds true for u when the measure of the boundary is small. What kind of functions have this property?
Riemann integral functions.
Yes. So it's very interesting that when one learns calculus, and many of you may have learned calculus, like what the Riemann integral is, even before college, but in any case, it's something long forgotten. Once you learn the Lebesgue integral, you think, now I can set all of that aside because I know a much more powerful tool of integration. Well, in fact, this theorem holds when f is Riemann integrable. And indeed, when f is not Riemann integrable, you can make a counterexample to a slight generalization of this result. So the correct hypothesis here is that f is Riemann integrable. And the idea of content that I mentioned, which predated Lebesgue measure, is kind of the analog of the Riemann integral for the indicator functions of sets. Okay, so that's a little nuance to be aware of when we're discussing uniform distribution. Okay, so now I'd like to change gears slightly and discuss in detail a hyperbolic toral automorphism. And we're going to give proof that it's mixing. That's very different from what we've done already that used Fourier analysis. This proof will be very robust. So we now go to the setting where x is our torus, and t from x to x is a hyperbolic linear automorphism. In other words, it's given by t in, let's say, SL2Z or GL2Z. I'll say SL2Z for completeness, with eigenvalues. And again, just for concreteness, I'll say lambda greater than 1 over lambda. And of course, there's then a vector such that TE is lambda E, and another vector so that TE prime is E prime over lambda. And since T is integral, it's actually a homeomorphism of the torus to itself. It preserves Lebesgue measure, but there's some topology going on. So let's give a topological picture of this dynamical system. So first, in R2, we should probably just forget the regular basis elements. It's the regular, we can draw the integer lattice, but should probably just forget the coordinate axes, if they have no real meaning. But what does have meaning are these eigendirections. So there's a line in the direction of E, and then there's another line in the direction of E prime. And this line is expanded by a factor of lambda. The restriction of the map to this line is multiplication by lambda. And then there's a different line. And the restriction here is to multiplication by 1 over lambda. So the dynamics is highly contracted. Now, I probably should have chosen different color for the second line. Anyway, so let me make it, try to fix that. Okay, so the mapping is diagonal with respect to the basis coming from these two eigenvectors. So it preserves the foliation of R2 by horizontal lines. I mean, not by horizontal line, but by parallels of the expanding direction. And it also preserves the foliation by parallels of the contracting direction. So all the red lines are set to red lines and the blue lines are set to blue lines. I'm not saying the red lines are set to themselves, not at all, because the blue lines are being contracted. And so a red line that doesn't go through the origin is moved closer to the origin and then expanded. And then it's moved still closer and expanded even more. And now if we were to go down onto the torus, well, there's two possible ways to say what that looks like. One would be to just take a fundamental domain here and remember that the sides are identified and maybe fill in the foliations a little bit more. And the other would be to really try to draw the torus itself as a geometric object. And then what you'll notice is that since these vectors are contracted or expanded, there can't be an integer point on this line through the origin. The slope of E has to be irrational. If there was an integer point here, it would have to be set to it itself or it's negative. Anyway, the eigenvalue couldn't be bigger than 1. So what we see if we look at just this line through the origin is a geodesic on the flat torus. And in fact, since it has irrational slope, it's dense. Even just one leaf is dense on the torus. So the red lines give a dense foliation of the torus, and then the blue lines give another foliation of the torus, making a constant angle with the red lines. And also invariant under the action of T. And the dynamical system preserves all of this structure. Now let me point out something about these two foliations. I defined them using linear algebra, but you can define them using dynamics. So let's suppose we take 2 points, x and y, on the torus, and I'm going to discuss one of these averaging things. I'm going to discuss the sum of f along an orbit x. And actually, I'm going to discuss 2 kinds of sums. So I'm going to discuss the sum in the positive direction, and I'm going to discuss the sum in the negative direction. So this will be, as usual, 1 over n, the sum from 0 to the n minus 1 of f. But now I'm going to take it as f of t to the plus or minus I of x. So sometimes I'm going to sum along the positive direction. Sometimes I'm going to sum along the negative direction. And f is continuous, and I'm going to take f to be continuous. Okay, so now suppose I take 2 points on my torus, and they have the following amazing property, that as you go forward in time, and let me call the orbit of this x0 and y0, x1, x2, x3, etc. As you go forward in time, the orbits get closer and closer together. The orbit of y is shadowing the orbit of x. So what we do is we say x is equivalent to y if the distance of the ith iterate of, if in forward time, ti of x and ti of y converge. Not that they converge to the same thing, but that they converge to each other. They get closer and closer together. And when x is equivalent to y, then, well, we can now form, and we can now take our torus and we can break it into the equivalence classes for this relationship of asymptotic and forward time. Now, what would be good about things being asymptotic in forward time? So what you'll notice is that if you change x to y, and they are asymptotic in forward time, then since f is uniformly continuous, the values of f at x sub I, at t sub I of x, are almost the same as the values at t sub I of y. So what we find is that if x is equivalent to y, and let me put a plus here to remember that it's in forward time, then this implies that the averages for x and the averages for y are almost the same. So the difference between these averages tends to 0. They're going to give the same value for sampling, the same kind of sampling of our function x. Okay, now when are 2 points asymptotic in forward time? Are there any points that are asymptotic in forward time? Well, there are. You see, if you pick 2 points, let's do an example. If I take x and y on this blue line, then as I start applying the map, the blue line is contracted by a factor of lambda. So as I iterate, these 2 points both converge to 0, but in particular, they get closer and closer to each other. Now, that has nothing to do with the fact that the line went through the origin. If I took x and y here on another blue line, then their image would be on a different blue line, but the blue line itself would have shrunk by a factor of lambda. So here's x0, y0, and then here's x1, y1. They're much closer together, and so on. So what we see is that the equivalence relation here, the equivalence classes for this forward time asymptotic relation, just correspond to the leaves of the blue foliation. And so this blue foliation, let me call it F plus, this is also usually denoted by Fs, this is called the stable foliation for T. And notice that I define this foliation only using topology. Its leaves consist of points whose orbits are asymptotic in forward time. And then, as you can imagine, the red lines just correspond to pairs of points, the equivalence relation of being asymptotic in negative time. So we defined x is equivalent to minus y. Similarly, we get a foliation f minus. Okay, now we're almost done. We're almost done with the proof that this transformation is ergodic. So I have to erase something. So let me erase the setup here, and then I'll state Hopp's theorem, and I'll do the proof. So the theorem of Hopp is that T is ergodic. Okay, now what is it that we have to show to prove T is ergodic? All we need to show is that so by the ergodic theorem, so let f be a continuous function. So by the ergodic theorem, we know that Sn fx tends to some function f bar of x, ae, as n goes to infinity. And in fact, since f is bounded, it's in L2. This is in L2 of x. And we know exactly what this function is. It's the projection to the invariant functions. And so ergodicity is equivalent to saying that no matter what f we chose, f bar is constant. Well, of course, constant AE, because we might not get convergence everywhere. Okay, now what does the ergodic theorem tell us? The ergodic theorem tells us that when we do the sums over the orbit starting at a given point, that these sums converge to f bar of x, at least for almost every point we started with. Well, actually, these sums are not well defined, I have to say whether I'm going in forward or backward time. But in fact, I don't. The projection of f onto the invariant functions doesn't depend on whether or not you're going forward or backwards. So in fact, the forward sums converge to f bar almost everywhere, and the backward sums converge to f almost everywhere. Nevertheless, let me call the limit of the forward sums, let's say Sn of f plus or minus, this tends to some function f plus AE, and Sn, f plus or minus AE. And what we just proved was that if x and y are on a blue line, if they're on the same leaf of the stable foliation, then the values you get for f plus are the same. So again, something has to go, sorry. So the first statement is that if x is equivalent to y in forward time, then this implies f plus of x equals f plus of y. And of course, these are both equal to f bar of x. And this equivalence relation is just the same as saying x and y are in the same leaf of the blue foliation, which was f plus. So what we conclude is that this function f bar is constant on blue leaves. And that's by reasoning with the forward iterates of t. But by exactly the same reasoning, we conclude that if x and y are asymptotic in minus time, then f bar of x is equal to f bar of y. And so what we get from that is that f bar is constant on red leaves. Okay, so let's think about what this is really telling us. Now remember that f is just a measurable function. Let me emphasize that. So this is measurable and bounded. We want to have a little bit of tameness. But this function has the property that when you look at it in one of these local charts that's foliated by red and blue lines, not sure where blue went to. Yes. That it's constant AE when restricted to almost every red line, and it's constant AE when restricted to almost every blue line. Well, a little measure theory allows you to conclude the obvious thing, namely f bar is in fact constant AE. So this in turn implies t is ergodic, because the ergodic averages of every continuous function converge to a constant. Okay, so let me sum this up again, because it's a very powerful argument that uses no Fourier analysis or anything like that. I have a dynamical system, and I observe that when I take the ergodic averages of a function, it doesn't depend on, it depends only on what happens in distant forward time at this point, but it also depends only what happens in distance backward time at this point. But those two events are independent of one another, so it doesn't depend on anything, and therefore it's constant. Okay, that's the idea of Hoff's proof, is that this ergodic average, whatever it is, it's so unstable. The past orbit of x has so little to do with the future that it must just be a constant function. Okay, so that's the formal proof. And this argument has a further step, which we'll discuss next time, that will allow us to prove that f is mixing. So since I only have 1 minute left, let me just give you a little bit of a warning or of an interesting example of where we're using the fact that f was a measurable function here. You might say seems almost like f could have been any kind of function, but somewhere there's some AEs and you really have to use some measure theory to finish the proof. So let me just finish with an interesting example from set theory. So if you assume the continuum hypothesis, that this implies there exists a total ordering of the interval from 0 to 1 such that for all y, the set of x, which are less than y, is countable. Now you might think that's crazy. How could you, the whole interval is uncountable. It has the cardinality of the continuum. How could all of these initial segments be countable? Well, let me give you a counter argument. Consider the integers. The integers have an ordering such that every initial segment is finite, and yet the union of the intervals, the integers are infinite. So if the cardinality of the continuum is just the first cardinal that comes after the countable sets, then in fact there exists such an ordering. That's what the continuum hypothesis guarantees. And now if we admit this, then we could construct a set E, which is the set of pairs x and y, such that y is bigger than x. So this is an amazing subset of the square. And it has the property that if you cut it with a vertical line, given by some point x, Lx intersect E has measure 1 on that line. In fact, this part down here is just countable. So it's the complement of a countable set. And if you cut it this way, well, the same thing is true, but in the reverse, the measure of Ly intersect E is equal to 1 for every y. So here's a subset of the square. Every slice in either direction is measurable. The horizontal slices all have measure 1, and the vertical slices all have measure 0. Sorry, one of these was wrong. This should have been measure 0. So this is just to illustrate that without some assumption like measurability, this last step in the theorem wouldn't work. And in fact, Fubini's theorem actually has some content. There are sets such that all the slices of those sets are measurable, but the set itself is not measurable, and it has this kind of paradoxical property. Okay, so next time we'll finish the proof of mixing, a la Hop, and then we're going to start on hyperbolic geometry of surfaces. So please start reading chapter 4 in the notes, which will be on this topic. Okay, and as usual, I'll hang around in the Zoom room for a little while. Thanks.